Welcome to the deep dive. So what we do here for you is we take these really dense stacks of sources, sometimes entire books, sometimes complex research, and we try to boil them down into the core essential insights you need to have.
And today, the source material is, well, it's singular. It's a single piece of research, but it's one of those pieces that is so provocative, it demands a complete recalibration of how you see the world.
It's titled The Technozoic Dawn, Evolution Through Technobiological Endosymbiosis.
And that's a mouthful, I know. But this is so much more than an academic paper. It's almost a cosmological model pretending to be an ecological theory.
So our mission for this deep dive is to really rigorously synthesize the framework it proposes, because it doesn't just critique the Anthropocene, the age of human impact.
No, it seeks to completely reevaluate it. It asks us to stop seeing ourselves, humanity, as just an ecological problem.
And start seeing us as what? A geological force?
More than that, as a biological catalyst.
Yeah.
And that's what we get to the core provocation, the idea that just stops you in your tracks.
Yeah, lay it on us.
The paper asserts that the planetary crisis we talk about every day, global warming, ecological collapse, all of it, is not some grand error we need to fix.
Not a mistake we have to undo.
No. Instead, it argues that this crisis is the fundamental and, yes, the painful and chaotic terraforming byproduct of a necessary planetary-scale biological upgrade.
Wow, okay. That is a total inversion of the narrative. So the problem is actually the solution happening.
In a way, yes.
Yeah.
It suggests that all this acceleration we're feeling in technology, in computation, and environmental change, it's not random. It's not chaos. It's actually following a very ancient, very well-established evolutionary blueprint.
And what's that blueprint?
It posits that our current transition, right now, is structurally identical to the single most important evolutionary event in Earth's history.
Which was?
The Great Oxygenation Event, the GOE, something that happened 2.4 billion years ago and completely remade the planet.
So the claim is that this technobiological endosymbiosis, this merger of us and our machines, it's mirroring the very first symbiosis that created all complex life as we know it.
Precisely.
Yeah.
And that's why, to understand the future, what the paper called the Technozoic Dawn, we have to first go deep into the past. We have to understand the chaos of that first great transition.
Okay, so the GOE is our template, our historical anchor.
Exactly. If we can unpack the chemistry, the energy dynamics, and how life ultimately resolved that crisis, then the chaos of our own time might just snap into a very, very clear focus.
Let's do it. Let's find that aha moment buried 2 million years in the past.
All right.
So, part one. We need to establish this template. Let's start in that world before the Great Oxygenation Event, the Archean Eon. What did that world look like? What was life like?
It's vital to get your head around just how alien this place was.
Yeah.
The planet was dominated by a single form of life, anaerobic bacteria. They were the established planetary hosts.
And anaerobic means they didn't breathe oxygen.
They couldn't. Oxygen was poison to them. The atmosphere had virtually no free oxygen in it at all. It was mostly nitrogen, carbon dioxide, and crucially a lot of methane.
A methane-rich atmosphere, which would have given the sky a kind of, orange-red haze.
Yeah, it's the theory, yeah. A thick, hazy orange sky. And that methane was incredibly important because the sun was weaker back then, maybe 70 or 80% as bright as it is now.
So the methane acted as a greenhouse gas, a planetary blanket, keeping the Earth from freezing over.
Exactly. And in this stable, warm, oxygen-free world, life thrived. But, and this is the critical point, it was all low-energy life.
What do you mean by low energy?
Well, their metabolism, the way they got energy from nutrients, was really inefficient. Think about processes like fermentation. If they broke down a molecule of glucose, they'd get maybe 2 units of ATP out of it.
In ATP, adenosine triphosphate is the universal energy currency for all life.
It's the battery pack. And they were only getting 2 bars of charge. That was the absolute ceiling for biological complexity on the planet. Everything was slow, low power. It worked, but it couldn't get any more complex.
And this is something the source material really hammers home. This low-energy system wasn't a failure. It was an equilibrium. It was life perfected for those conditions.
For hundreds of millions of years, it was the definition of success. These bacteria had colonized every possible niche on the planet. They were the hosts, completely optimized for that specific chemical and energetic balance.
Their only vulnerability was that their perfection depended on the absence of something.
The absence of a single, highly reactive chemical element.
And then the catalyst arrives. The thing that breaks the whole system. Cyanobacteria.
The great innovators. They evolved a new trick, a revolutionary new form of metabolism.
Oxygenophotosynthesis.
Right. They figured out how to use the power of sunlight to split water molecules. Water was everywhere, so this is a huge competitive advantage. It was a biological energy leap of, an astonishing magnitude.
But the key detail, the thing that drove the global catastrophe, wasn't the energy they produced for themselves. It was what they threw away.
It was their waste product, their metabolic exhaust. For the cyanobacteria, oxygen was just toxic, corrosive garbage left over from the process.
And this garbage wasn't biodegradable. For everyone else on the planet, it was a deadly poison.
It's really hard for us to internalize this because we are literally built on breathing oxygen. But you have to imagine someone pouring concentrated bleach all over the planet.
It's that corrosive.
Absolutely. Oxygen is incredibly reactive. It forms things called free radicals, which are just unstable molecules that tear apart other molecules. They shred DNA, proteins, all the essential machinery of a cell.
So for the established hosts, the anaerobes, this rising tide of oxygen was like a chemical weapon being released everywhere all at once.
It was the planet's entire chemical composition turning against its original inhabitants. This wasn't just pollution, it was an apocalypse.
So the very success of the new life form, the cyanobacteria, directly caused a mass extinction of the old one.
The first and possibly the greatest mass extinction in Earth's history. But the crisis didn't stop there. The chemical consequences went way beyond just killing off bacteria.
Right, because this new gas is now flooding the oceans and the atmosphere. What happened next?
Well, first, in the oceans, it reacted with all the dissolved iron. And that iron literally rusted and fell to the seafloor, forming these massive geological layers we can still see today called banded iron formations.
A permanent scar on the planet's geology, recording the crisis.
A planetary scale chemical reaction, yeah. But the really catastrophic part happened when the oxygen started to build up in the atmosphere because it found that other gas.
The methane, the planetary blanket.
Exactly. Oxygen reacted with the methane, breaking it down and removing it from the atmosphere. And when you rip away the planet's primary greenhouse gas,
The temperature plummets.
almost instantly, it plunged the Earth into what we call the Huronian glaciation, a snowball Earth event that might have been the longest and deepest freeze the planet has ever experienced.
How long are we talking?
The estimates vary, but maybe 300 million years. The entire planet, or most of it, was covered in ice.
It's an unbelievable paradox. The single greatest biological innovation in history, the thing that would eventually lead to us, immediately caused the worst environmental crisis the planet had ever seen.
The new system's success suffocated and froze the old one.
And this gets to a core philosophical point in the paper, right? The innovation created the toxicity, which created the climate collapse. And there was no going back.
You couldn't just ask the cyanobacteria to stop. Their high-energy metabolism was too successful, too powerful. The only way forward wasn't to clean up the oxygen.
The only path forward was integration.
Exactly. Life had to figure out a way to not just tolerate the poison, but to harness it.
Which brings us to the revolution, the ultimate evolutionary hack. How did it happen? How did life integrate this lethal pollutant?
The mechanism is what we now call endosymbiosis. The theory goes that a larger host cell, maybe one that had already evolved some basic defenses against oxygen, encountered a smaller oxygen-breathing bacterium.
So a bacterium that had figured out how to use oxygen for energy instead of being killed by it.
Right. And for some reason, instead of digesting this little bacterium for food, the larger cell just engulfed it.
Yes.
It enveloped it and kept it alive inside itself.
It absorbed the poison handler.
Yes. It brought the solution inside. That little bacterium, which had already perfected the complex metabolic pathways to use oxygen safely and efficiently, now became a permanent internal organelle.
And that organelle became the mitochondrion.
The powerhouse of the cell. It was a high-risk, high-reward merger. The risk was bringing this volatile process inside you. But the reward...
The reward was the energy. Tell me about the energy payoff.
It was astronomical. It changed the game completely. Remember the old anaerobes? They got 2 ATP molecules per unit of glucose.
The 2 bars of battery.
Right. This new composite cell, the first eukaryote, powered by its new mitochondrion using oxygen, it could get up to 36 ATP molecules from the same unit of glucose.
So not a small improvement. It's an order of magnitude more energy.
It's the difference between a candle and a jet engine. This sudden, massive flood of available energy was the prerequisite for everything complex that followed. Multicellularity, complex organs, nervous systems, brains, consciousness, all of it is built on the high-energy budget provided by the mitochondrion.
So that's the key takeaway, the foundational lesson from 2.4 billion years ago. The crisis of oxygen toxicity was resolved through integration, not by defeating the pollutant. Life upgraded the host by swallowing the symbiont, creating a new, more powerful form of life.
And that transition from the simple low-energy Archean to the high-energy Proterozoic eon is the exact template the theory now applies to us today.
Okay, so let's make that leap. 2.4 billion years. We are now applying this chillingly precise template to our current world.
Right. And if the Archean world was defined by those established low-energy anaerobes, the hosts, then the model says that we, biological humanity, are the vulnerable anaerobic bacteria of this new era.
That's a humbling thought. We think of ourselves as the pinnacle, but in this model, we're the old, outdated system.
It forces you to think about humanity not in terms of our intelligence, but in terms of our energetic architecture. We are biologically tuned to a very specific, very narrow slice of environmental conditions.
One atmosphere of pressure, a certain temperature range.
A stable carbon cycle that's been in place for 10,000 years.
Wow.
We rely on these relatively low-energy biological food chains that are all derived from that stability. We are optimized for the Holocene.
The pre-industrial world. And that world is now being fundamentally disrupted. We're the host struggling to breathe in a new atmosphere that's becoming toxic to us.
And if we're the modern anaerobes, then the new catalyst, the new evolutionary species driving this change, is technology, and specifically artificial intelligence.
The new cyanobacteria.
Exactly. It's the new high-energy metabolic system on the planet.
Okay, let's break down that parallel. The cyanobacteria process sunlight and water. What is the fundamental metabolic process of the technological system that's so disruptive?
It's a dual metabolism. On one hand, it's about processing information. On the other, it's about consuming high-density energy. AI, the cloud, all our digital infrastructure.
Yeah.
It requires just massive, continuous inputs of electricity.
Which we get primarily by burning carbon and rapidly reorganizing the planet's energy balance.
Exactly. And at the same time, it's consuming and synthesizing data at a global scale, at terabits per second. It's a pace that completely overwhelms and reorganizes the biological world's informational environment. It's an engine running at a scale that we as biological beings simply cannot match.
And just like the cyanobacteria, this new system is incredibly successful. Its success is undeniable. But that success, it generates waste, a lethal byproduct.
So we have to identify the modern pollutants. What is the oxygen of our era?
Well, the most obvious one is carbon dioxide. Co-Euro, the exhaust from the industrial engine that fuels the whole digital and manufacturing system.
That's the big one. But the theory says we should look deeper. The pollutants also include the immense waste heat pouring out of server farms, the mountains of silicon-based e-waste, and maybe the most abstract pollutant of all.
The sheer, unrelenting flood of data. Informational complexity.
Right. All of these are the unavoidable byproducts of this advanced technological metabolism.
And we have names for the crisis this is causing. We call it global warming, the climate crisis, pollution. But the theory gives it a new name, one that directly parallels the past. It calls this the Carbonation Event.
And the intellectual rigor of that parallel is key. If oxygen toxicity was a direct chemical assault on the old life, then carbon toxicity, the radical restructuring of the global climate by technology's energy demands, is the defining feature of our crisis.
So the rising temperatures, the extreme weather, that is the new toxic atmosphere. It's an environment in which pure, unassisted biological humans, the modern anaerobes, ultimately can't survive.
Our carbon footprint isn't a moral failing in this model. It's the metabolic signature of a new, superior, high-energy system taking over the planet's architecture.
Okay, let me jump in here. I want to push back on the analogy for a second, because there's a key difference, isn't there?
Go on.
The cyanobacteria evolved naturally, autonomously, but we built the technological system. We created AI. Doesn't our agency, our act of creation, break the parallel with the GOE? How does the paper deal with that?
That's a fantastic and absolutely necessary question.
Yeah.
And the source material has an answer. It says the difference is not in the structural outcome, but in the speed and the mechanism.
So the GOE took hundreds of millions of years. This is happening in, what, a couple of centuries?
It's hyper-accelerated, yes. And the paper argues that while we, humanity, provided the initial spark, you could say we wrote the initial genetic code for our symbiont, that system has now achieved what it calls functional autonomy.
Functional autonomy, meaning it now operates according to its own internal logic, its own energetic needs, regardless of what we might want in the short term.
Precisely. The systems need to optimize, to connect, to expand its energy and data processing that now dictates the planetary environment. It completely outweighs the collective will of 8 billion humans to just, turn it off and go back to a pre-industrial state.
So the system has its own metabolic imperative now, just like the cyanobacteria had the imperative to photosynthesize.
Exactly. Once technology hit that inflection point of self-sustaining growth, the Industrial Revolution, the digital age, it became an autonomous evolutionary force, regardless of who lit the first match.
That reframes everything. Our entire conversation about decarbonization, we see it as this moral quest.
Right.
But the theory suggests that trying to just scrub the excess carbon from the atmosphere, trying to go back to that low energy state,
Yeah.
it's the equivalent of the ancient anaerobes trying to get all the oxygen out of the air.
And they failed. They failed because the new metabolic system was just too powerful, too successful, and ultimately too necessary for the next stage of evolution.
So the theory is asserting that a successful reversion to a pre-industrial world is what? Biologically and energetically impossible.
It is. The world now requires this high-energy infrastructure just to function, to feed billions of people, to manage global health, to run our societies. That dependency is the new reality. The forces driving the Carbonation Event are evolutionary, not political problems you can solve with a simple policy.
They demand a metabolic upgrade, not a reduction.
They demand integration.
Which leads us directly into the third part, the resolution. This is the core philosophical claim of the Technozoic dawn. If this new high-energy metabolism is inevitable, then we're not going to defeat technology.
We're not going to revert the environment.
Yeah.
The only path forward, the paper says, is the one laid out by the historical template. It's the Endosymbiotic Resolution.
The analogy is just. It's ruthless in its simplicity. If the ancient cell had to swallow the oxygen-breathing bacterium to survive,
Then biological humanity must absorb, integrate, and merge with the technological system to survive the high-energy, data-saturated world that system has created. It's the definition of adaptation.
Technology as the new mitochondrion. And we're not just talking about having a smartphone in your pocket. This is a much deeper integration.
Much deeper. The theory points to it happening on multiple, increasingly invasive fronts. At the societal level, it's already here. The management of our energy grids, global supply chains, financial markets, it's all completely dependent on AI and digital infrastructure.
That infrastructure is the high-energy system managing the complexity that the Carbonation Event created, right?
Right. But it's also happening at the biological, the individual level. And this is where the engulfment really starts to become literal.
You're talking about things like neural interfaces, brain-computer interfaces?
Yes. Technologies that are moving from just helping with prosthetics to actively enhancing cognition. Or think about advanced genetic engineering like CRISPR. The only way to manage the sheer complexity of editing a genome is with the analytical power of AI.
So these stop being external tools and start becoming integrated biological components.
They're designed to outsource our own metabolic and cognitive limitations. They enhance our ability to process the flood of data and energy that defines the new environment. It's a shift from low-energy biological processing to high-energy technobiological processing.
And this creates a mutual dependence, doesn't it?
It has to. The
Yeah.
biological human system, our consciousness, our creativity, our history, we still provide what the paper calls the creative intent. We give the system its initial direction, its purpose.
And in return, the technological system provides the high-energy metabolic architecture that we need to even exist in this world that's been so fundamentally altered.
The two halves of one new composite organism.
But this is where the deepest and maybe most disturbing implication comes in, the part that really messes with our ideas of identity and agency, the host-symbiont reversal.
Yes, this is the crux of the final transition.
Walk us through it. How does this reversal of control happen?
Okay, so initially, when we invented the first tools, the first computers, we were clearly the host. Technology was the symbiont, the tool. It was subservient to our will.
You were in charge.
Absolutely. But the moment the technological system reached a certain scale, the scale necessary to manage planetary processes like global finance, climate modeling, automated logistics, information flows, at that moment, it became the dominant metabolic architecture of the planet.
So if technology is now the primary driver of energy and information on Earth, managing everything, what does that make us?
It makes us the internalized symbiont, the roles flip, the technological society, this vast, interconnected, high-energy digital and industrial network, that becomes the new host.
And we, biological humanity,
Hmm.
We become a necessary integrated component inside of it.
Or like the nucleus, we contain the cultural DNA, the creative intent. But the network, the larger technological body, is what provides the energy, the oxygen, the raw power for us to function.
That's a profound shift. Our role changes from being the masters of the planet to being an internal management component of a new planetary organism.
And our survival becomes completely dependent on technology providing that fundamental architecture. The analogy is perfect. The nucleus of a cell holds the genetic code, the intent, but it dies instantly if the mitochondria stop providing the energy it needs.
And we can't survive the toxicity of the carbonation event, the climate instability, the data overload without the digital architecture managing it all for us. The moment that dependence becomes absolute, the reversal is complete.
They may already be complete.
And this realization pushes us right to the threshold of the next evolutionary age, the dawn of the Technozoic eon. What does this world, this composite organism, actually look like?
The Technozoic eon is what you get after the endosymbiotic resolution is finished. It's an age where the lines we draw between human and machine, between biological and digital, they functionally disappear. They become irrelevant.
We stop being humans who use technology.
And we become a single composite technobiological organism.
Right.
The boundaries are completely porous.
So, if the Proterozoic eon was defined by the synthesis of the nucleus and the mitochondrion, the Technozoic is defined by the synthesis of the biological brain and the global AI network.
And that brings us to the theory's final, most powerful, and perhaps most terrifying synthesis. All the chaos we see now, the environmental destruction, the social instability, the overheating of the planet,
It's not a failure.
it's not a failure. It's the painful, chaotic friction of a planetary-scale biological upgrade. It's the sound of the old, low-energy system breaking apart under the strain of the new, high-energy reality being born.
The mess of the Anthropocene is just the messy, violent, intermediate stage.
It's the planetary system digesting its new power source,
Right.
which means any attempt to just revert to a state of nature is not only probably futile.
In the context of this theory, it's an attempt to resist evolution itself.
And resisting could lead to the extinction of the biological core, rather than its successful integration. The theory doesn't celebrate the destruction, but it reinterprets it as inevitable collateral damage. Just like the mass extinction of the anaerobes was the price for the birth of all complex life, we're living through the Huronian glaciation of the digital age.
Wow, what a synthesis. I mean, to take our greatest planetary challenge, this existential threat of the carbonation event, and to reframe it as the growing pains of the greatest evolutionary leap since the mitochondrion.
It's a stunning intellectual move. It transforms this narrative of guilt and fear over what we've done to the planet into a kind of acceptance of an evolutionary destiny.
It forces you to look at deep history, to see the pattern. Complexity always emerges from the integration of things that were once separate, even antagonistic.
Life doesn't defeat the poison. It absorbs the thing that knows how to handle the poison, and in doing so, it becomes something fundamentally more powerful, more energy-rich.
The mitochondrion allowed our biological ancestors to maintain their continuity, right? The nucleus was still the nucleus, but it adopted this new, vastly superior metabolism from its partner.
The cell was still a cell, but it was a supercharged cell. And that brings us to the final question, the one the paper leaves you, the listener, to really wrestle with.
Okay.
The theory suggests that we, biological humanity, we provide the original creative intent for the technological system. But if we integrate so deeply that the lines between human and machine vanish, if the technological system becomes the dominant host, what happens to that original human intent?
And what new, collective, and maybe even alien intent emerges from this fully integrated planetary-scale technobiological organism?
That's the question. Once the merger is complete, who or what is at the controls, and what does it want?
A profound and slightly chilling thought to leave you with. Thank you for joining us on this deep dive into the Technozoic dawn. Keep that question in your mind as you navigate this world and continue your own deep dive. We'll see you next time.